and welcome to the NPTEL online certification courses. Under the course Digital Control in SMPCs and FPGA based prototyping, today we are going to study digital control implementation using microcontrollers and specifically the Texas Instruments TIDM-02008 reference designs overview. The concept covered in today's lecture will be TIDM-2008 design overview, the specifications and feature set of TIDM-2008, the key control differentiations techniques implemented using C2000, as well as the test results and observations. So what is TIDM-2008 basically? So TIDM-2008 is a GaN-based interleaved continuous conduction mode operated totem pole bidirectional PFC. Fundamentally, the reference design can be used as a power factor corrector or a grid-tied inverter based on the supply side that you provide. Leveraging C2000 capabilities for basic as well as advanced control techniques such as phase shedding, adaptive dead time, AC drop will be something that will be covered through the course of this lecture. The image that you see here on the bottom left is the actual hardware board design that is presented. On the right that you see is the schematic. To deep dive a little bit into the schematic, what we see on the left side in the actual design is 3 inductors. They are the filter inductors. On the bottom side of the image that you see are the high frequency GaN bridges. There are 2 inputs provided to the design, AC input as well as DC input. Based on what you want to operate, if you are operating in the PFC mode of operation, you would want to provide AC input, and if you want to operate at a inverter level, then you will provide DC input. There is a control card presented in the design, and there are 6 GaN bridges LMG3410. In detail, we will go through the C2000 microcontroller implementation using TMS320F 28004X device. So fundamentally, the TIDM-2008 feature set includes 3.3 kW single phase design with an operating frequency of 100 kHz PWM. It has a programmable output voltage feature. Additionally, its operating TSD is less than 2% and an efficiency of greater than 98%. One good thing is that the same source code can be maintained when running from C28X core or the control law accelerator as discussed in the previous lecture. If you are using the control law accelerator, you free up the C28X core, thereby adding the additional bandwidth for the C28X. The applications include the onboard chargers for electronic vehicles, the telecom rectifiers, drives, welding and other industrial equipments. It can also be used in energy storage systems. The attractive part about this particular design is its higher power, higher efficiency and higher power density. So the TIDM-2008 specification includes the input voltage of 120 or 230 volt with a frequency of 60 Hz or 50 Hz if operated in the PFC mode. If you are operating under the inverter mode, it has a 380 volt DC bus nominal voltage as the input. Input current will be 16 ampere RMS or 10 ampere RMS based on what mode you operate. Same way, if you are operating in PFC mode, the input voltage of inverter mode will become the output voltage of PFC mode. That is 380 volt DC bus nominal voltage will be the output voltage of the PFC mode. Same way, the AC 120 volt RMS 60 Hz or AC 230 volt RMS 50 Hz will become the output voltage for the inverter mode of operation. Output current, same way, 10 ampere maximum or 16 ampere RMS maximum for PFC mode and inverter mode respectively. The power rating will go from 1.65 kW if operated at a single phase 120 volt RMS or 3.3 kW at single phase 230 volt RMS. The current TSD will be somewhere around 2% when operated at rated load. The efficiency is around 98.7% at 230 volt RMS and it will be somewhere around 98% again at 120 volt RMS. The peak efficiency when operated in inverter mode is 98.3%, whereas if you are operating at 120 volt, it is somewhere around 97.3%. The primary filter inductor as per the calculation comes around 478 microhenry, whereas the output capacitance comes somewhere around 880 microfarad. The PWM switching frequency kept for this particular design is 100 kHz. So moving on to the control side of it, the TIDM sensing parameters that we need for the control are input AC voltage, that is the line to neutral voltage is highlighted. Then there are 3 inductor currents, so IL1, IL2 and IL3 as highlighted in the picture. Then there is AC input current that we are sensing, and finally the bus voltage as shown here on the right. To control all these things, we use the TMS320F TIDM-02008X device for sensing, control as well as processing. There are three additional parts to this. One is the LMG3410, that is the GaN power stage. The UCC27714D that you see on the bottom left is actually the low side gate driver, and there are two FITs, sync FIT as well as the active FIT. These parameters will be used for additional control. So moving on, the first and foremost important part is the protection. So we'll be sensing a lot of currents, so IL1, IL2, IL3 AC currents in this circuit for the protection purposes. So first of all, I would like to compare between the conventional analog control with the digital C2000 control. So the image that you see here on the top left is basically representation of the analog control. The right image, the two right images that you see generates the reference for the PWM trip signals, I trip low as well as I trip high. That will be fed to either the negative input of the comparator or the positive input of the comparator. We have the I inverter feedback coming in, which will be compared with the references generated, and based on the actual status of the current, that is the I inverter feedback current, we will generate the PWM trip if the current goes beyond a certain limit or it goes below the certain limit. Now, this requires quite an amount of complexity in terms of design. If you are opting for a digital controller, digital comparator, what happens is that you get an analog input, you throw it to the ADC, ADC will give you a digital output, and that you can use, that you can feed into the internal comparator available with the C2000 for overcurrent protections. The blue shaded DAC L value and DAC H value that you see are basically the DAC resistors, which can be user programmable. So you need not have any separate circuit that we used to have for the analog part of it. We can simply feed in the value in the resistors, and based on which we can have the comparators. The comparator output can be fed to the PWM module, which ultimately can generate the PWM trip. The advantages for going to the C2000 CMPSS are basically the onboard space reduction, the cost advantage since you do not use any external circuitry, everything is there on board, and specifically lastly, it enables the fast tripping of the PWM since it's hardware connected internally. The control block diagram of the TIDM-02008 is represented as shown here. The bottommost part that you see, that is the plant and sensing, the topmost part is the voltage loop, and the middle part is the inner current loop. In plant and sensing, what is there is the sensing part of the circuit. So it will feed all the sensed signals to the voltage loop as well as the current loop. The voltage loop has a band reject filter, or a notch filter rather, which will generate ultimately a AC current reference and feed to the inner current loop. The inner current loop ultimately processes the data and generates the duty cycle required for the PWM and feeds it back to the plants and sensing. This is the overview of the control block diagram of TIDM-02008. The control loop frequency response observed looks something like this. The red line that you see in the images 1, 2, 3 and 4 is basically the modeled control loop that we designed. And the blue line that you see is captured using the software frequency response analyzer, that is the SFRA tool available with the C2000 digital power SDK. As you can see here, the blue line, that is the measured line, is almost matching the model that was as per our desired result requirement. And in the current loop as well as voltage loop, the gain margin as well as the phase margin represents that the loop is pretty much predominantly stable as required. So the test results that we see here, the startup was somewhere around 880 volt, and then we moved on the steady state power of 3.3 kilowatt. The DC bus voltage ripple observed during the steady state was nearly 12%, whereas the current TSD comes around 2.69 at the full rated load and an efficiency of 98.7%. So there are a couple of differentiations that we implemented using the C2000 device. The first differentiation is the AC drop test. So as an example, in the first, second and third image that you see here, if let's suppose the line cycle drops out, what happens is that when it again comes back, the PLL requires certain amount of cycles for synchronization back with the grid voltage. So what happens is that we lose certain number of AC cycles for which goes in the synchronization purposes. What a proposed solution dictates is that if let's suppose the line cycle drops out for whatsoever reason, we'll generate a virtual AC signal that is there within the MCU to consider that as a reference for the PLL. So as an example, Let's suppose that line cycle dropped out at some particular instant as shown here in the image. Automatically, the reference will be taken over by the virtual signal that is generated within the MCU, and as and when the line voltage comes back, automatically we don't need now the PLL, but we have already the virtual AC signal generated within the MCU which will do our job for the PLL, which can generate the required result. So that ultimately saves the number of cycles lost for the PLL synchronization. Now this result has been tested, and the test results are shown as here. So the test condition was that the AC input provided was 120 volt, the load was kept around 900 watts, the AC drop period that we kept was 1.5 line cycles, and the AC drop was started at 90 degrees, that is at peak of sine wave, and it was brought back at 270 degrees, that is the worst case again scenario at 270 degrees. The proposed solution as shown here enables fast detection of AC dropback events even in the worst case scenarios, and the input current immediately becomes sinusoid and in phase with the voltage. Moreover, what you can see here is that the current spike at T1 and T2, that is basically when the dropout event occurs, when the PFC freezes, and when the PFC resumes back, you can see that the current also is below a certain limit. Definitely, the voltage bus that you see here, the yellow colored image, the voltage bus will definitely start reducing because there is no input voltage V grid available. So that will slowly come down to 0 if this condition, the drop condition, remains for too long. Coming to the next differentiation, that is the adaptive dead time control. So in normal FET conditions, what happens is that if you have a fixed dead time, then there are chances that you have a spike in current. So spike in the IL peak. So what we are trying to do here is that you have COS Q2 and COS Q1 for sync and active FET respectively. What we are trying to do is that we have the COS value already defined, we know the voltage across the COS that is going to happen, and we know the current through the sync FET. So what we will try to do is that we will calculate the charging time or discharging time required for the capacitor across the sync FET. Based on the discharging time, we will keep the optimal dead time that is required for the sync FET. Using this, what we can achieve is the ZVS for the sync FET operation. Same thing cannot be applicable to the active FET, because active FET, the current passing through the active FET will vary depending on the mode of operation. Sometimes it may be IL peak, sometimes it may be input current as well. So that active FET current is not predetermined, and hence the same concept of calculating the optimal dead time is not possible in the active FET. So even if we achieve the dead time control for Q2, that is the sync FET, we will still be able to increase the overall efficiency using the ZVS. And additionally, one question may arise that what about COS? Is it always constant? Definitely there will be some variance, but TI-GaN has very small variance as compared to others in COS, and it enables adaptive dead time control implementation. So this is the formula that will be used to calculate the optimal dead time. As you can see here in the image, there are 4 parameters that we considered. One is the efficiency versus load, the second is efficiency difference, the third one is power factor, and the fourth one is THD, and we have compared both. One is without the adaptive dead time control, the other one is with dead time control. With dead time control is represented using the blue line, and without adaptive dead time control, that is using the conventional dead time, we have represented it using the red line. You can clearly see the difference in the efficiency versus load curve, that at lower percentage of rated load, we have significant improvement in the efficiency, whereas as you move towards the higher end of the load, the difference in improvement reduces. That same thing you can see here in the image that is on the efficiency difference image. So let's suppose if I look at a 0.55% of rated load, then the efficiency difference observed is nearly 11.5%. But that 11.5% efficiency difference doesn't remain the same when the rated load increases, when you operate at a higher load. For power factor as well as THD, we have observed similar performance. Then last differentiation is the phase shedding control. So the concept of phase shedding is basically that if you have light load, you would not want to operate all the 6 switches in parallel, because ultimately that will introduce certain amount of switching loss, that will introduce certain amount of complexity. What you would want to do is that if there is a light load operation, then you can only use a single phase and eliminate the other 2 phases. When you are having a little higher load, that is mid load, you can use 2 phase interleaving operation, and for heavy load you can use 3 phase interleaving operation. thereby reducing the number of switches based on the load conditions. Specifically, it does not have any major impact on the heavy load side, but for mid load you can see a smaller improvement, and for light load perfectly it will give a greater amount of improvement. So this concept is also implemented using C2000, and the observed graphs are shown here. So same way we are showing the graph of efficiency difference, the THD as well as the power factor. The first thing that I will take up is the efficiency, and as told before, we are able to see significant improvement in the single phase operation. So the blue line that you see here is a 3-phase interleaving operation, and the red line that you see here is a phase shedding operation. So in phase shedding operation, we can see a significant difference in the efficiency percentage. Specifically talking about the single phase operation. Then moving on to the 2-phase operation, that is the mid load condition, we don't see a significant improvement, and as and when we move forward to 3-phase operation, that is full load condition, it almost becomes similar to the 3-phase. It has to become similar to the 3-phase interleaving operation. The same thing can be observed on the image on the right in the graphical manner as well, where around 12% improvement is seen in the efficiency at lower rated load, that is nearly at 0.6% of rated load operation. As you move towards 20-25%, the efficiency difference goes on reducing. The THD also has been observed that it significantly reduces, and power factor has been observed to be almost similar. So coming to the conclusion part, there are certain references which you can take up. So one is the C2000 Digital Power SDK. Within that, we have provided all the calculations required for using your inductor, capacitor, as well as some other parameters. And in additional, you can go to the TIDM-02008 product page, which gives all the details about the design guide as well as some other schematics that are relevant. One more device that we used was the GaN LMG3410. So I've marked the relevant context page over here. And lastly, the C2000-based software development kits, that's the fundamental development kit used in all our softwares that you can download from ti.com. In conclusion, today we studied TIDM-02008, that is the bidirectional totem pole PFC design overview, its specification and feature set. And lastly, we understood about the key control differentiation techniques, that is the basic as well as advanced technique using the C2000 software. Thank you.